to AP Biology Teaching Tips. I'm Joy Killow. In teaching tip number 7, I will work through theory and calculations of water potential. This video can be used with students by turning off the sound and pausing where appropriate. Water potential is a measure of the tendency of water to leave one place for another. It's represented by the Greek letter psi. Water potential lets us predict which way water will move, particularly into or out of a cell. Water always moves from a higher water potential to a lower water potential. In AP Biology Investigation 4, plant material is used to explore water potential. Students may have trouble with the concept of higher and lower in terms of real numbers that go above and below zero. If scaffolding is needed, use a number line to illustrate higher and lower numbers. The more positive the number, the higher the water potential, the more negative, the lower. Knowing that water moves from a higher water potential to a lower water potential, students should predict which way water will move. After predictions, advance to show the animation and discuss. You are looking for an explanation that uses water potential value. Give students this question to ponder. Ask them to explain their answer. They may realize that they have to know something about the water potential of the sucrose solutions. Point out that this is good insight. Then proceed with the next 4 slides for predictions. They should improve on each slide. Which way will water move here? Predict and explain in the table groups. After the animation, ask if their predictions were right. Repeat the predictions, discussion, animation, and formative assessment here. Repeat again at equilibrium. Be sure they note that water is moving in and out of the cell, dynamic equilibrium, and that the water potential of the cell and the solution are the same. And one last time with water coming out of the cell, but still following the rule, water moves from higher to lower water potential. What exactly is water potential? Water potential is the sum of 2 components, pressure potential and solute potential. Point out and show students that this equation is on the formula sheet. As water enters cells, the cell contents press on the cell wall. The cell wall exerts pressure back. Increased pressure makes it less likely that water will enter the cell. This pressure potential is usually a positive value. The addition of solutes makes solute potential more negative. A cell or a solution with a high concentration of solutes has a more negative solute potential. The water potential is the sum of these 2 values. Water potential can be experimentally determined. Let the students begin to ponder this, and after about 5 minutes, debrief. Using larger pieces of tissue from plants, like a French fry-sized cylinder made with a cork borer or baby carrots, lets us multiply the effects of one cell so that the results become more visible to us. Have students consider these questions if plant material is placed in different sucrose solutions with these different water potentials. How will the plant tissue feel? How will the mass or the length change? This is another slide that invites students to think about what they know and how to put it together. It's possible to determine the actual water potential of cells at equilibrium if you collect information about the behavior of cells in solutions with a variety of molar concentrations, because molarity is a measure of the amount of solute in a solution. A bigger molarity means more particles, resulting in a more negative solute potential. This is usually done with percent change in mass, but percent change in length works too. You will likely need additional scaffolding for most students from the next few slides. Lead them to the idea that when the plant tissue is neither gaining nor losing mass, the water potential of the cells in the tissue is equal to the water potential of the solution in the beaker. And then show them mathematically what that relationship looks like. Given that these are equal, can we solve for the water potential of the potato cell at equilibrium? First, we note that the pressure potential in an open beaker is 0. So solute potential plus 0 equals the water potential of the sucrose solution at equilibrium. This means if we know the solute potential, we know the water potential of the sucrose solution. And since the water potentials are equal at equilibrium, it's also the water potential of the cells. So how do we figure out where equilibrium is, and how do we determine the solute potential? Do we have to make 100 solutions? No, we make a spread of solutions, and then we calculate percent change in each of those. Then we do a best fit line, looking for where the line crosses the x-axis. We take that down to the sucrose molarity, and we can calculate here on this best fit line a sucrose molarity of about 0.36 molar sucrose. So to calculate the solute potential, we use a formula on the formula chart, negative I CRT. I is the ionization constant. For sucrose, it's 1 because sucrose doesn't ionize. C is the molar concentration, which we got from the best fit line right here where it crossed. This is our C. The pressure constant R is given, 0.0831 liter bars per mole Kelvin. And then the temperature must be converted to Kelvin, so it's important to remind students to take the temperature of the solution before they dump their solution out. Here's an example. The solute potential is negative ICRT. Remember, it's on the formula chart. This is negative 1 times 0.36 moles per liter for the concentration, the constant, and then the temperature of 295 Kelvin. This gives you negative 8.83 bars. It's a unit in pressure, and this equals the entire water potential of the cell under these conditions. At this point, you could revise your definition of osmosis to include water potential. And remember, water always moves to a more negative water potential. This has been Teaching Tips in AP Biology. Until next time.